Welcome to this second lecture on an online mathematical course on elementary differential geometry. So last time we saw so last time we saw that gamma t gives a parametric equation of a curve which is same as giving the coordinate of a point at time t in R2 or R3. Okay, so basically we can think of gamma t as a position vector of a point at time t. More formally, this t belongs to an interval which is a subset of R. Now, for the values of t, say t belongs to open AB, so the position vectors for all t in AB will give us a curve, or more formally, this curve will have a trace in R2 or R3. So now we will look at some examples to make this more precise. So for example, we have been given a curve y square minus x square equals 1. So this is the Cartesian equation of the curve which is a specific case of the hyperbola. It's a vertical hyperbola, right, centered at 0, 0. All right. So we need to find a parametric equation which describes this level curve as we defined in the previous lecture. You can notice it is of the form fxy equals a constant c. So in order to do so, we need to find so you need to find the gamma of t, we need to find gamma 1t and gamma 2t such that gamma of t can be written in terms of gamma 1t comma gamma 2t. So as we saw in the last lecture, this is basically the x and y coordinates of the points or a particular point lying on the curve y square minus x square equals 1. Since we have defined gamma from R to R2, the value of this coordinate in R2 corresponding to this gamma will be dependent on the choice of variable from this domain. That means the x coordinate is a function of t and the y coordinate is a function of t as well. So in order to avoid confusion, I named x as gamma 1t and y as gamma 2t. Alright, so to repeat myself, the x and y coordinates will depend on the parameter t, because for a particular time, say at a particular time t naught, we have a point here, and corresponding to this we have a point here. Alright, so these 2 points are unique for t naught. Alright, so x is a function of t and y is also a function of t. More precisely, gamma 1 is a function from R to R where it takes t to x, or which is basically gamma 1 of t, and gamma 2 is also a variable in one function in one variable which takes t in R to the y coordinate, which we define as gamma 2 of t. Okay, so for this example, y square minus x square equals 1, we need gamma 1 and gamma 2 such that this equation is satisfied. Now recall from high school, we have several trigonometry identities. Cosec square theta. Now these trigonometric identities prove to be quite useful for us when we are trying to find the parametric equations. So notice this is the equation or identity which we might be needing in order to find gamma 1 and gamma 2. So let's define gamma 1 as tan t and gamma 2 as sec t, where gamma 2 is y and gamma 1 will be our x. So from this identity, y square minus x square is sec square t minus tan square t, which is equal to 1. Hence, gamma t is given by tan t comma sec t. Now, an important thing here to notice is that t lies from minus pi by 2 to pi by 2, and now this is essential because the trigonometric functions are periodic in nature. Also, sec square is 1 by cos square, and 1 by cos pi by 2 is undefined. Hence, we are not using the equality symbol here, and this I leave it as an exercise to plot on some online graphing calculator like GeoGebra or Desmos, and put these value for the parameter, and you will see for yourself why is this essential. I would suggest to play around with these value, and you and try to analyze and grasp how the curve changes. Okay, now moving on to another example. We'll So this was the parametric equation for a hyperbola. Now more generally, a hyperbola is of the form y square upon a square minus x square upon b square equals 1. So in that case, we'll take our x as a tan t and y as b. I'm sorry, my bad. X would be b tan t and y would be a sec t. Y is a sec t. Okay, now we look at another example for an ellipse. So say we take an ellipse x square upon 4 plus y square upon 9 equals 1. Here we will be using the much popular trigonometric identity of cos square t plus sine square t equals 1. So let x now technically I should write x as a gamma 1 of t, but now, from now on, for the sake of convenience, I'll refer this to as x only. So it was meant to clear the theoretical background and framework running behind, and to make sure that it's not forgotten that the coordinates depend on the parameter t. So x can be defined as 2 cos t, and similarly y can be defined as 3 sine t. Then x square upon 4 plus y square upon 9 is equal to sine square t plus cos square t. Okay, I'm sorry. Well, it doesn't matter, but cos square t plus sine square t equals 1. Notice that these terms will get squared up and they will cancel out with the denominators. So the parametric equation for the ellipse is, for this particular ellipse, is 2 cos t and 3 sine t. Now more generally, in place of 4 or 9, the general Cartesian equation for ellipse is x square b square. Okay, so here we can define x as a cos t and y can be defined as b sine t. Okay, now after doing some examples for finding the parametric equations, maybe we should do some examples where we are given with a parametric equation and we have to find the Cartesian equation. So for example, our gamma t is given by e to the power t. This is the exponential. I'm sorry for my bad handwriting. This is not epsilon. I have a ancient style of writing the letter e. So this is the exponential to the power t, comma t square. Now it is a good exercise to plot this on an online calculator and see how this curve behaves. So here clearly this is xy, all right? So we can write x as e to the power t and y is t square. Okay, so we need to express one variable, that is either x or y, in terms of the other. So for x equals e to the power t, we'll take the log on both sides. So we'll get this. So now the notation I'm using, ln x means log base e x. Okay. Now substituting this in this, we get y equals ln x square. So this is our desired Cartesian equivalent equation of okay. So I guess this is a good example. One last example I would like to uh, deal with is, it's nothing complicated or something fancy about. It's just a very common, it uses a very common technique which we will find in many problems and exercises, while parametrization problems we will find. So we'll try to find the parametric equation of a cycloid and the parametric equation of a very special curve. It's historically very relevant, known as the witch of Agnesy. Now, this is no witchcraft related thing. It's, to my knowledge, it's a translation from Latin to English. I'm not very sure of this fact. I read it somewhere online, so I would heavily emphasize that this needs to be verified. Okay, so I will like to give you a hint and as an exercise to try on your own, but surely I'll discuss this in my next lecture. So for a cycloid is, so this is a circle, not a very good circle. So cycloid is the path traced by a point P on a circle which is translating along the x-axis without slipping. That means it's an ideal motion of a circle without any friction or any other resisting forces. So it looks like something like this. So this is what is known as a cycloid, and it goes and it repeats. It's a periodic thing. So the point traced by this path traced by this point P is known as the cycloid. If I would heavily strictly and like to emphasize that one should look up the animation for the cycloid. So plot online and see how this works, or watch some animation. It's available on Wikipedia, YouTube, etc. Anywhere. Now the basic idea for finding the parametric equation, we a key for finding to parametric equation is to make the appropriate figure, and we are done halfway. Once you have the figure, the correct figure with you, we can easily manipulate and come up with different mathematical stunts in order to prove what we want. Okay, I'm sorry, this is a very bad circle. Okay, so this is a circle we have. Say this is the point P, which will trace our cycloid. Now from the origin, and say this is the center of our circle. Now we'll do some kind of construction. So this is our angle theta. This is clearly 90 degree. This is the radius r. This r is the radius of circle. All right. Point Q. So we need to find the coordinates of this point P, X, Y. Now remember that this circle is not only rotating about its axis, that is from the center, but it's also moving in the forward direction. That means after a certain time it would be somewhere here, and this point P would have moved from here to say here. All right, so this is a figure at a particular time t naught. Okay, but since this t naught is arbitrary for us, the result we will reduce will hold for all t. Okay. So I need you to think about this as an exercise. Maybe this cycloid thing might not be very clear, so I would strongly suggest that you visit some online graphing calculator and plot it and watch some animation to see and get an idea how exactly point P traces the cycloid. So, but in order to solve this problem, we don't need anything like the, it's a hint that we don't need the fact that the circle is moving. However, it is indirectly hidden that the circle is moving because theta would change. So find something in terms of the theta. So because this theta would ensure that a circle is moving uh, along the x-axis. However, for a fixed theta, we need to find the coordinates of the point P, x, y. And then again by this logic that since this theta naught would be an arbitrary, in a particular domain, this theta naught will help us traverse through the x-axis and our cycloid would be plotted. So I would like to end this video here and would like you all to work on this exercise on cycloids, and we will see how exactly we can compute the cycloid, and we will discuss some further concepts. Till then, keep learning mathematics and enjoy mathematics. Thank you so much. Feedbacks and criticism welcome. And if you have any special requests about any specific question or any other exercise, you can drop it on the comment section. Thank you.